It's nice to see you back. We had a little bit of a break last week. And before we get started today, I'll just draw your attention to item 4. We won't get all the way to the end of the slides that I prepared today, but almost to the end. But just to let you know, we'll have a small homework. I'll try to get it activated by dinner time or hopefully before that. A small homework assignment about the stuff that we talk about today. But before we get to the subject of heat, I want to go through some of the grading situation with you. And to do that, I want to do some clicker questions. So get your clickers on. And let's refresh our minds with some grading concepts that hopefully you remember. %. And just so you know, good, you guys are here. We have a ton of clicking today. We're going to have about 19 questions. Well, maybe I'll round off to about 10. We're going to have a ton, so I'm glad that everybody's here. A ton of questions. So question, April, do you have a clicking? You still have that clicker? Okay. All right. Question number 1. How many midterms exams are on the schedule this semester? If you don't get this one right, you have to explain it to Napoleon Dynamite. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, we got a ton of clicker questions. Get your guys' clickers ready. Yeah, 98% of you got it right. It's 3 exams. I don't know how. I guess 3 people got caught napping. Anyways, we got 3 exams. Now, this is going to be important for the grading process that I described today with you guys. Okay? 3 exams. Now, we've only had 2 so far, but we got 3 on the schedule for midterm exams, plus a final. All right, another thing I want to bring up, your roundup score. Remember, we break this down. This is not in itself a number of points that you have. It's a code. The decimal part tells you how many answers you've clicked in successfully. So for instance, for this student, 34 clicks. All right? And you can look yours up in the decimal part of the roundup number. And the whole number part tells you how many you got correct. Because every time I ask a question, I indicate the correct answer. All right, so I'm clicking both of those. And so remember that those 2 numbers break out of the thing that you see inside web courses. Now, as far as clicking goes, let's see how your mind recalls this. To get 25 out of 25 automatically, what do you have to get? $20 seconds to vote. Hurry up. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Did you get it? Okay. I got a bunch of people that voted for C. No way, Jose. D is the correct answer. If you got C, if you answer C, you might be thinking about, I don't know what you're thinking about. This is the famous leeway factor. So if you've answered 85% of the questions for the semester, you're automatically, and I'm going to show you how to do that today, you're automatically going to have 25 out of 25. If you're below that, you might have 23 out of 25 on clicking. Right? So if you have 70% answered, you're not out to lunch. But you might have 23 or something like that. But answer in general. At every point in the semester, you can figure out how many answers. Well, every time I publish your roundup figures. All right. Now, our next question. We've talked about this factor before as well. Bonus points. See, because this is why I break out the whole number part of that roundup figure. I want to look at that. And this applies at the end of the semester, but we can still think about it now. "20 seconds. Do not let me catch you napping. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, okay, good. Let me see. What's the correct answer here? Some of you voted for 85%, but the threshold for this is 75%. Yeah, so if you get a B, so if I took all your clicker questions and put them into, like a test, and you get a B on your test, then you get 4 bonus points. All right, now, calculation time. Hit the refresh key, if you will. We're going to do a numeric question here. It's money time. November 31st. You want to calculate your regular participation pointage. Something out of 25. Your section has had a total of 90 questions. And we might be up at 90 by that time. At least how many must you have answered to lock in? Now give me a whole number. Gosh, don't type in. Boy, this looks like the genius section. I caught the maybe not. Maybe not. Students, don't round off. Think. A whole number that you need to break 85%. To hit 85 or higher. It's got to be, because you can't, don't answer like 17.2, because your answers are going to be a whole number of answers, not 17.2 answers. "30 seconds. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh, yeah, pretty good. 85% of you got it correct. 77 is the correct answer. And for those, 15 of you typed in 76. Okay, 76 does not break 85%. It's close, but it's not 75. And that's how I do it. And I look for the number that breaks, Now, if we have 100 questions exactly, then it's 85 straight, But if, we're probably not going to have exactly 100. So by the end of the semester. So this is the calculation that you're going to want to do going into finals week. And I'll try to show you how to do that here in a second. So let's take a look at the grade estimate situation for you guys, where we are now with grades. Okay, so we've got 2 midterms. Go ahead and jot this down. This will be helpful for everybody. Just make this part of your notes. This way you can look at I can tell you, if you ask me in web courses, I'll say check your notes. All right, so we've got 2 midterms on the books right now. 50 points each, total of 100 possible. But we haven't dropped anything. We keep the best 2 and drop the lowest. But we haven't dropped anything yet because exam 3 is not on the books yet. All right, so keep working and hustling and bustling. All right, come to class on time, click faithfully, do your homework on time, and get ready for exam 3. All right, now, for this section, the number of questions that we have on the books as of the 16th is 37. Now, today we're going to be asking another bunch of them, so that's going to be up to 40-something here in about an hour when we're done. But for what I've uploaded into web courses, 37. Now, hey, you guys, do not get caught napping because the other section, the 9 o'clock section, they've got 39. All right, and I'll be try to get you guys caught up today with a couple extra questions, and then everybody will be the same again. But for right now, 37. So that means the 85% level, which you guys just calculated for 90 questions, for 37, it's 32 or more. So if you look at your roundup figure and it's something .32 or higher, then ding, that's 25 out of 25. You don't have to do anything more. All right? But if you're below 32, you got to use the proportion. Now here's the proportion that you got to work out. It's not that bodacious. You put in, how many answers you've got up here in the numerator and divide by, that should be divided by 37. Sorry about that. I'll try to change that if I can. So that should be your answers divided by 37. Then divide that by 0.8. Anyways, figure out, proportion, whichever way you like to do. Except use 37 in that left-hand side. Okay. Now, the 75% bonus level from 37 questions is 28. So if you have 28 point something or more, ding, you'd get 4 bonus points if today were the end of the semester. Now, you don't get bonus points. You don't get jack until the end of the semester anyways, but this is how you can estimate, your grade for right now. Okay? And it's actually possible, if you think about it, to have less than 25 on your regular points. So you might have 24 out of 25 and then get if you have 28 out of 37, then that's above 75, but it's not above 85%. So you can actually get a bonus even if you don't have full 25 out of 25. I never thought about that before, but it's possible. So anyways, you can calculate all that stuff out. Now, I haven't figured out this bonus point thing, and I haven't put that, and I won't put it on until the end of November. But you can figure out, what you got right now to figure out your grade status for the, the end of October. The thing about it is, this number, 37, is going to be changing for us. It's already changed because we've already asked about 3 or 4 questions. So it's going to be changing. So you might get back on, if you're off the 25 out of 25 scoreboard right now, you might get back on it after today if you're here and you click on everything, So it just depends. This stuff will change. Now, homework. We have had a ton of homework, and you guys have been really good, most of you. Now, I'm not going to look at anybody, but some of you are still not registered with the textbook website. That's your business. Some of you don't have any points from the textbook website because you biffed up your NID. You got to go in and do that. But for for all the web courses and Great River homework, total is 197. So for this one, just multiply your percent. So however many points that you've got from homework, homework, and don't count homework 0 or homework double 0. By the way, you're going to have homework 000 tonight to ask you about the exam 2 printouts. So you're going to have actually two tiny homeworks tonight. Hopefully not too grievous. But don't count double 0 or 0 in with your homework points. And then just round that up to the nearest whole number, or round it up to the next whole number. So here's your calculation. So this one's a little bit easier. You don't have to do a proportion. You just got to do a percentage and then multiply by 25 and round up. And homework and the clicking pointage is the same. I always round up. Give you guys the benefit of the point. So if you have 23.000001, I round it up to 24. Homework-wise and participation-wise. So if you look at this, this is a rundown of what we've done so far. Right now we've got 150. Now that's regular points. That's not including bonus points. Now the early iClicker registration bonus points, some of you have all 4 of them, some of you only have 1, some of you don't have any. But if you have any, you can add those in to the numerator. So add those in as well. If you feel bold and you've got the 4 points bonus from clicking, add that in. But that might evaporate if I catch you napping on too many questions between now and the end of November. So don't get a big head. And that is why I don't post that bonus point until the very end of the semester. All right, because I don't want anybody to make a mistake about that. All right, questions? April, do you have a question? Okay. No, I just, I thought you were checking your homework figures or something with those guys behind you. Okay, is that what you guys are doing? Okay. All right. Now, just a note, as I mentioned, things are going to change. We're probably going to be closer to 100. Right now we're at 37, but we're going to be we might not make 100. We might go over 100. It just depends. So just get down to business. We're in the last lap before finals. And then at the finals, then your finals sprint. All right? The homework, oh my goodness, closer to 400. So things can change. But for right now, here's the grade scale that you want. Until the final exam is on the books, Rachel, we have a basis of 150 points. So for everybody that's been to both exams, this is the grade scale that you want to think about. Right? Not the one on the syllabus. The syllabus is when everything's on the books, including the exams. But until then, 135 points or more, and some of you have got that. A bunch of you have got that. B, 113 points or more breaks you above 75%. C, 90 points, and 75 points or more for D, and below that it's an F. Now that's on the basis of 150 regular points. Now don't forget you can add the bonus points, but that doesn't increase the basis. You know, so if you, for instance, a student that didn't make it to exam 2 or that had an exam 2 blooper and we recovered, they don't have a grade right now, and we dig out their Scantron and find out what the score was and then add it in, that's going to add 50 points to the basis. They're going to go from a 100-point basis to 150, which is where most of you are now. But adding in bonus points, you know, figuring out you got 4 bonus points from clicking, that doesn't add to the numerator. You stay at 150 for the basis. Right now in web courses, this is important information. And if you've looked on web courses on your grades page, you've got homework and clicker pointage up there as of October 16th, actually as of October 11th. No, as of October 16th when the last homework assignment was due. So it's all in there now. Now those you know, that's going to change today because you got clicking today, and it's going to change Thursday because you got homework due Thursday. So, but for right now, as of 10/16. And a couple things I want to point out to you. The very top line is basis up here, all right? Now that means the number of points possible for you. If you've been here for both midterms, that's 100, and then you've got homework and clicking on the books, that's another 50, so a total of 150. Now almost everybody in here is at 150. So you use that grades table that we just looked at. If you're on a different basis, if you've missed exam 1 or exam 2, you'll be on a 100-point basis. And you'll look on this row of your grades page and you'll see where you stand. Okay, and hopefully it'll make sense to you. Now some of you were absent for exam 1, but you were here for exam 2. Good. Some of you were absent for exam 2, but you were there for exam 1. Good. You're on a 100-point basis. And that being the case, you don't go by that table that we just looked at. You have a different table of grade estimates. And if you look in discussions, you'll see it. Okay, I put a little thread in there about the different bases. Right, so now, unfortunately, I cannot make this top line up here automatically become this number down here. It looks like it's automatic here for this student, but it's not. And unfortunately, Canvas is not a real spreadsheet. It's just like a list of data. It's a homework data base. It's not a live spreadsheet. So I can't put 100 up here in the basis and then have that show down here in the out of number. And this is another reason why I deactivate stuff like averages and grades in web courses. Because if I was to put, you know, just putting this information, I want you to have this information, the basis that you're on for grades. And most of you are on 150. A few dozen of you are on a 100-point basis. I want you to have that. But unfortunately, Canvas doesn't give a hoot about that. They just add the points in willy-nilly. And because that's the case, there's all kinds of misconceptions if I leave the grades and averages and stuff activated. And that's why I deactivate them. I don't want you guys looking at, oh man, I got 1,700% for my semester grade, you know, when it's not really possible. But for web courses, you don't. If you ask web courses Canvas, they don't know the difference. But we know the difference. That's why I'm going over it with you right now. By the way, somebody asked me in web courses about the average for the test. It was a little bit below 70, so 69 point something, as I recall. So it's, you know, the exam one was a little bit above 70. I try to get a 70% average for the exam. And if I do that, you know, so I adjust the number of basic questions and brain burners and stuff. This was a tough test, though. You know, you guys didn't break 70 on average. And the real test of how tough it was, or the real sign is, nobody aced it in either section. There were good grades, but nobody got 100%. So, but you know, your total points for the semester are looking pretty good. That's the second line here. So if you're above 135, by hook or by crook, whatever method, ding, you got an A for today. And that can all change by the end of the semester, because we got about 2/3 of the semester ahead of us, or excuse me, 2/3 behind us, 1/3 ahead of us. All right. So let's take a look at the schedule, and let's just go over. Oh no. This is wrong. This is right. Okay. Here's you. I forgot to take out the section 1 slide. This is you guys. All right. So lecture 19 is today, October 23rd, and 20 on Thursday, October. And then Wednesday, office hours all the way down, ditto marks, until exam week. Final exam week is the last row of this table. So lecture 27 is Tuesday, November 20th. And it's not a lecture, it's an exam. You know, but we'll meet here, you know, just like for exams. And then that Thursday, I won't be giving you that day off, but UCF will be. It's Thanksgiving Day, so everybody will be off on that day. That's in green. And lecture 27, exam 3 in yellow. And then the final exam. Now you guys have a more humanistic or a more humanitarian schedule. The other guys, section 1, they have a 7 a.m. final, but you guys are 10 a.m. So I don't want anybody to, if you're late for this final, I don't know what to tell you. Newbie freshmen, I know you're out there. I know there's a bunch of yous. Do not try to be a senior and stay up all night studying. Monday night, December 3rd. Because then your 4 alarm clocks are mysteriously not going to work. I've never seen Murphy's Law, whatever can go wrong will go wrong at the least advantageous time. Murphy's Law strikes freshmen every time. See, you know what I'm talking about, right? But I know you're not a freshman, but you've seen it. I mean, you know that there's certain individuals in this world that have been freshmen in the past. And I'm not going to ask a show of hands, but I'm sure everybody here has seen friends or even your own experience where you just, you know, you lose it. And for those of you guys that are newbie freshmen, it really is a factor. It's a physical factor. And it might not catch up to you on Monday or Tuesday of exam week, but the stress that you go through, physical stress, you know, just staying up late to study, that's physical stress. It's going to do 2 things. It's going to degrade your performance on the final exam that you do take, if you get there. And 2, it's going to drop a bomb on your immune system. So you might find yourself on Thursday of exam week when you have that big final for economics class, and you're going to be suffering with some kind of nasty virus or something. God forbid you're in the emergency room or something like that. But that can happen. I even had a friend, when I was in grad school, one of my buddies was in, undergrad. And he told me that one time when he was a freshman, final exam week, he ended up he was studying for his exam, and the next thing he knew, he was in the emergency room with a bunch of intravenous tubes hooked up to him, stuff. He had passed out. And it wasn't anything other than he was dehydrated. He was dehydrated from too much Mountain Dew and coffee and everything like that, monsters. And so try not to get caught napping by that. All right, questions about this schedule? Yes, Rosie. Finals are cumulative. Finals, our final, everything from August to end of November. November 29th, inclusive, so. Axel.
We have some sort of study guide for the final posted on web courses or no?
Study guide, you say? No, Axel, we don't have study guides in this class. Your so-called lecture notes are your study guide. That's my. Yeah, I never. Oh, you were asking for a friend. Yeah, okay. Yeah, tell your friend. No, I know. But we'll have a bunch of reviews. Matter of fact, the weekend going into finals. So lecture 29 on November 29, that'll be our last lecture. I'll give you, hopefully in that lecture, we'll have a little review set that we do here with clickers. And then that weekend, a big mega review homework and web courses. Kind of gets you, warmed up for the final and stuff. So, but no, I never get a study guide. But you've got study guide materials from lecture and also from the exams and the blurb sheets. By the way, I'm going to do one more 00 or 000 homework assignment to see who wants their exam printout. So, the PDF. So that'll be part of your homework tonight too. All right, now I want to give a little bit of a summary concerning the topic of brain burners, where we are, where we're heading. There's a set of brain burners that I like to teach about every semester. Stopping time and stopping distance, for instance. It's a classic skill that it's important to know, to distinguish between the two. And I caught a bunch of you napping that you were asked for a stopping distance and you calculated a stopping time or vice versa. I can't remember what you guys had, but I know a couple of you guys got caught napping. Free fall table of energies. Get the downward speed. Yeah. I don't think I asked that on exam 2, but we still have the final. Heat melt heat, which we're going to start today. This whole idea of heating up ice, melting it, and then heating up liquid water or any other substance. We're going to start tackling that today. Another classic brain burner from semesters of the past is calculating the thermal equilibrium temperature. How do two, you take a cube of ice, and some water at room temperature, and what's the final temperature going to be? Well, it depends on how much liquid water, how much solid ice you have, and what the initial temperatures were and stuff. We'll be tackling that problem. Another thing that we'll be doing is nearest neighbor interactions, and that is going to be when your neighbors are protons and electrons. In other words, simple models of molecules and the interactions of the electromagnetic force between protons, electrons and electrons, protons and protons. And that's in a couple weeks. Okay, so we're going to be tackling that. And that's going to help us in the periodic table, which is our main topic, this is our final target. Also electron wavelength, which I've kind of already mentioned a little bit. That's another brain burner, not because it's difficult, but because it's kind of hard to fathom. It's, how can a particle behave like a wave? But electrons can, and we're going to be tackling that in the very end of November. So that's kind of some of the stuff that we've been through and some of the stuff ahead, so you can mentally prepare yourself for that. Now, there's one last topic from Chapter 5, the phase diagram, and this is actually a good place to put it because at the end of Chapter 5, beginning of Chapter 6, and heading for the periodic table, which is going to be Chapter 9. I'm going to introduce this today. It's already, if you've read the end of Chapter 5, you've seen it, the phase diagram. And it is a map. Sometimes you hear people call it a phase map or a phase portrait. Basically, it maps out the position of an object in motion, and the position or the coordinate is on the horizontal axis, like the x-axis here, and then the corresponding momentum. See, the x-coordinate is left and right, and if an object's in motion along the x-axis, it's going to either have some rightward or some leftward momentum, and so that's going to be positive p subscript x or negative p subscript x, and you map that out. And this is a special place called, it has its own name, it's called phase space. And it's completely abstract. This is not a picture that you can take a photograph of. It's a picture that you can use to think. And it encodes a lot of information that we're going to talk about today. But it itself is abstract completely. You cannot photograph it. Just as with the velocity graph. The velocity graph gave us distance rectangles and distance triangles. You couldn't photograph those, but you could use those triangles to think about positions and speeds and stuff, accelerations. And the same thing here. It's a very handy concept. Now, in phase space, if you have a periodic motion like uniform circular motion, and you map out the, uniform circular motion is going to have an x component that's periodically going, left to right, and it's also going to have a y component, on graph paper, but we're forgetting about the y component for now. The x component, it's going to be a bound motion, a bound system, and it will map out to an ellipse. Now, it doesn't have to be an ellipse. And in fact, my little sister's an electrocardiologist. And one thing I know that the cardiologists do, they take an EKG for somebody, but another thing that they do, so they look at the sinus rhythm. If you have a healthy heart, you got a sinus rhythm. If you have a heart murmur, you got little, curvaceous bumps in your electrocardiogram. The cardiologist can tell what that means, like one of your valves is not firing properly or something. But what they do is they make a phase diagram of your heart using an electrocardiogram. And they analyze it, and a sinus rhythm, a good steady heartbeat would look like an ellipse. But then, once they get everything adjusted right, it'll come out looking like an ellipse. But somebody with, a heart murmur or a valve or defibrillation or something like that, it's going to be a little bit more wobbly or even chaotic. Fibrillation is chaotic. It's not nice and neat like an ellipse. But a good sinus rhythm, a good regular heartbeat, yep. Now, the interpretation of the area is important for us. And that's what I want to emphasize today. When we were looking at the velocity graphs, a month and a half ago, those areas gave us distance calculations. The distance triangle, 1/2 AT squared. The distance rectangle, V times T. Right? That was an interpretation of the area. Now this one has different dimensions again. This is not a velocity graph, but it has an area that it's handy to analyze. So the width is in meters, and the height is in kilogram meter per second. So the area here, length times width, or width times height, and there's a formula for calculating the surface area of an ellipse like this. It's not hard. Meters times kilogram meters per second. Meters times kilogram meters per second. What physical quantity have we seen that has meters, kilogram meter per seconds? Think. Raise your hand. No, joule is kilogram meters squared per second squared. So this one's meters times kilogram meters per second. A distance times a momentum. Distance times a momentum. Now, where have we seen that before? Nope, a Newton is kilogram meter per second squared. Kilogram, let's see, meters times kilogram meter per second. Where have we seen that? And here's your ellipse. You're going to have a bounded over here on the left, a negative number for the x coordinate, and over here on the right you're going to have a bound. If it's a periodic motion, it's going to go back and forth. So like a spring going back and forth. Meters times kilogram meters per second. Where have we seen that? And then the upward and the lower bounds are momentum. So here's your maximum rightward momentum, P max. And down here, same size, if it's a good sinus rhythm, minus P max. Meters times kilogram meters per second. Where have we seen that before? How would that actually be? Kilogram watt per watt. Meters kilogram meter per second would be, rearrange it. What would you get? Kilogram watt per watt. Right, it would be kilogram meter squared per second. What's that measure? What physical quantity have we studied that's got kilogram meter squared per second? Impulse? No. Impulse is just kilogram meter per second. It's not impulse, it's not joules, it's not newtons. Kilogram meter squared per second. What is that? Kilogram meter squared per second. I can see people leafing backwards and forwards in their notes. Kilogram meter squared per second. I'm searching for somebody that raises their hand. You're going to get it. What do you got? Nothing? Not work. Work is kilogram meter squared per second squared. This is kilogram meter squared per second. Okay? Yeah, so joules is kilogram meter squared per second squared. But what we've got, the area here, so the area here might be 27.42 kilogram meter squared per second. What do we got? That's a quantity of what? Inertia, no. Inertia is measured in kilograms. What's that? Newton's second law, no. Ding, ding, ding. Angular momentum. All right? So write that down and put a big star next to it. Angular momentum. Okay, so here's your phase map, right? And the area of this phase map represents a dynamical quantity that we call angular momentum. But wait, there's more. You know, just like it says on TV at 3 a.m. when those infomercials come on. Wait, there's still more. From this, you can actually derive an oscillation or an orbital frequency. And I'll show you how to do that probably in 2 weeks. But this is where we're heading with this. And guess what? The reason that I'm pointing this out to you now is because this phase diagram is going to be eminently helpful for us when we tackle the periodic table. And you may say to yourself, Dr. B, the periodic table, that's electrons and protons and atoms and stuff. What does it have to do with the ice skater effect? Well, this is Max Planck. And he figured out Planck's constant, H. And Planck's constant is measured in units of angular momentum, kilogram meter squared per second. And this is the constant that rules the quantum world. In fact, it rules the universe. One constant to rule them all. Not Newton's constant, not the speed of light, but this constant. Every physical process is tied up with this baby. But you know, and we're going to use it to leverage the periodic table and figure out what the, you know, why the periodic table is the way it is. I mean, whoever said it had to be a table? How about color? You know, you guys that are in art, you know, you think of a color wheel, you know, a circle, you know, from starting at red, going through orange, yellow, green, blue, indigo, and then back to violet, and then back to red in a round circle. Why isn't the periodic table like that? Periodic table is a bunch of rows and columns. Max Planck's the one that gave us the technology to figure it out. But you know, he didn't start with electrons. Nobody knew about electrons in his day. You know what he was studying? He was studying heat. So let's talk about chapter 6. And now we're on the trail of Professor Max Planck. And he's up there. He's up the mountain. We're heading up the mountain, and he's up there. Come on, you guys, let's go. And here's another guy. You know, Max Planck had that nice mustache going. Here's James Prescott Joule, a British scientist. He's got the James Harden beard going. He's a very smart guy. And what he figured out is that there's a relationship between thermal physics, temperatures and stuff like that, heating and melting, and, you know, plain old mechanical 1/2 mv squared and mv and all that stuff. Now here's how he did it. He said, look, let me see if I can design an experiment that'll have a finite measurable amount of kinetic energy and some kind of a temperature change. And here's what he did. He set up, and this is kind of an idealization of what he had. He had a bucket of water or a beaker of water, and he had some little paddle wheels. And the paddle wheels were connected to this pulley system that you can see here. And at the other end of the pulley system was a weight. You know, so like 50 grams or, 500 grams. And he said, all right, I'm gonna drop this weight 50 centimeters. And that's going to correspond to a certain amount of MGH, a certain amount of joules of energy. And he said, I'm going to do that and then measure the rise in the temperature or change in the temperature of the water. And guess what? It always rose, and it always rose by a certain...
I don't know what you mean by, I'm going to do that and then measure the rise of the temperature or change. How about a website?
What? No. Gosh, series. It's getting a little nosy. Unbelievable. All right, now where was I? So he figured, he measured this, 6 zillion times, And he found the correlation. You know, the more mgh of potential energy, that when it's a kinetic energy of the paddles, corresponded to the temperature rising on its thermometer. And he said it was 1 for 1. They were proportional. More kinetic energy, more temperature rise. Gram for gram. You know, so if you have more water, it won't rise as much, but if you have less water, it'll rise more. But gram for gram, he found out that it, correlated exactly. And this is the basis for what we call the kinetic theory of matter, i.e., that the kinetic energy and momentum states on average of molecules in a gas correlate to these physical macro, and we can't see the molecules. We can't measure jack about an individual molecule of gas. But the temperature and the pressure are macroscopic measurements that we can make that correlate exactly to kinetic energy states and the pressure states of a gas in a container for pressure. But in this room, the average the temperature of the atmosphere in this room means that each, we don't know what any individual molecule is doing, but we do know on average what they're doing, a certain amount of kinetic energy. And that's what that's one of the many things that he figured out. Now here's another thing. Two different objects that have different temperatures, they're not in thermal equilibrium. And so that brings up the concept of heat transport, and that's in chapter 6, part 10. And the whole idea of melting and freezing stuff, and we're going to work on that today. Another thing is different elements and molecules, different substances in general, they heat up and they cool down differently. So H2O has different freezing points and boiling points than ammonia, and different again from CO2. And they have, they cool up differently. Some things are easy to cool off, some things are, like metal. Metal is easy to cool off. But, you can get it really hot and it won't melt, but, you burn your hand with it. But once you turn the heat off, it'll cool off rapidly. Water takes a long time. That's why my wonderful students, we get hurricanes not at the height of midsummer when the solar radiation in the tropics is the most, or in the northern hemisphere, the North Atlantic, is most intense. We get it here in September. September's the peak, and that's almost the autumnal equinox. That's like the peak of, and that's because water in the currents of the oceans of the earth is still carrying a huge amount of heat energy that doesn't cool off very rapidly. So it lasts until autumn, and we get these big storms. All right? So this has to do with the phases of matter, and how do we change from one phase to another, from solid to liquid? That's melting. From liquid to gas, that's boiling or vaporizing. Now, to understand all of this stuff in the kinetic theory and all the way through here, these heat concepts, we have to use something called the absolute or Kelvin temperature scale. Now, it's based on, now here's a picture of Kelvin. Lord Kelvin from England. He's got the good mustache going. All right? It's a metric system, temperature scale, but it's different from Celsius. Celsius is 0 at the freezing point of water. The freezing point of water is 32 Fahrenheit, 0 Celsius. The boiling point of water is 212 Fahrenheit, 100 degrees Celsius. But this scale is different. This scale is based, and here's a side-by-side comparison. Absolute 0 on the Kelvin scale is not the freezing point of water. It's actually the point where, colloquially you could say that all molecular motion stops. That's the 0 point, or that's like just, chatting around in the lunchroom language, not totally scientific. for absolute zero. We're molecular, because here in our in this lecture hall, we're breathing air, mostly nitrogen molecules and oxygen molecules, and a little bit of CO2 and argon and stuff, but mostly nitrogen and oxygen molecules, and they have a certain temperature. And we could, if it were cold outside, the warm air would rush through the doors outward. All right? It's probably hotter. No, it's probably not hotter. So if we open that door over there, warm air would move out. Now that motion, that transport, this convection, that's how you make a steam engine go. Except a steam engine, uses boiling water, and they get hot water vapor, steam, and it goes through the pipes, and it turns it's trying to go to the cooler area by way of the turbines. And the turbines spin, and they spin an electric generator, or they spin the screw of the ship that you're trying to move forward. And that brings us to the technical definition of absolute zero. It's the point from which work can no longer be extracted. Okay. Now we can get down to 0.01 kelvins. We can get down to 0.001 kelvins by a process of refrigeration. And it's not something that you could buy at the Home Depot, a refrigerator there, but there's methods that we can use to extract energy from a substance, thereby cooling it off all the way down to 0.001 kelvins. So we can do that. When you put a bottle of water in the fridge to cool it off, what the refrigerator does, it allows the heat from that bottle of water to expand, the freon, the coolant, in all the pipes that are inside the refrigerator, and and then that stuff in the cooling pipes drives a little, it exhausts energy out. It takes that energy from this to the coolant, and then it exhausts that out. And there's usually a fan on a refrigerator that blows out some warm air when it's running, when it's cooling. And that's what, that's a refrigeration process. And we can do that to 0.001 Kelvin. I think a little bit lower than that. But we can't possibly get to 0.000 ... We can't get to that because that's the point from which no work can be extracted. And, so there's no heat engine that will work, that will cool off anything, because there's no work to be extracted. All right. Now, here's the basic conversion combo. 0 Kelvin is minus 273 Celsius. All right. So if you should remember that. And here's the other one. This is the other easy one. 0 Celsius is positive 273 Kelvin. This is actually the one that I remember. And here's another easy one. If you remember number 4, you can remember number 5. 100 Celsius, boiling point of water, is 373 Kelvin. So this is why we call it based on Celsius. It's a metric system based on Celsius. And because there's still 100, there's 100 kelvins between boiling of water and freezing of water, 273 to 373, so 100 Kelvin. And hey, you guys, you don't usually say Kelvin degrees because it's not really a degree system. It's an absolute system. So you just say 100 kelvins. But each Kelvin corresponds to a Celsius degree somewhere. All right. And for this comparison, it's 0 to 100 Celsius. So 100 Celsius degrees from boiling to freezing, and 100 Kelvin from boiling. Versus Fahrenheit, it's 180. From 32 up to 212. And Professor von Fahrenheit, when he figured that out, I don't know, he had something in mind. I'm not sure exactly what it was. I think they weren't using ice water. They were using ice water mixed with salt which I think lowers the freezing point of water. So they were using a different freezing point, but we're not going to use Fahrenheit for anything this semester. But let's do a little simple workout. Get your clicker ready. And hit the refresh key, because this is multiple choice. Room temperature, 20 degrees Celsius. What does that correspond to on the Kelvin scale? So read carefully. And this is about as much as we're going to do with Kelvin, with Celsius. You know, in physics, like in astrophysics, my research area, we only think in terms of Kelvin because we're thinking about physical processes like nuclear fusion, which involves kinetic energy of little atoms and nuclei. And so we got to think in kelvins. We don't think in Fahrenheit, at least not for the last 100 years or so. And we don't think in terms of Celsius. Now, the guys on the Weather Channel, they're Fahrenheit and Celsius. But this class, we're going to be Kelvin all the way. Okay. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Get your click in. Okay. Yeah, you guys did good. 86% got that right. 293. And like body temperature, 96.8 Fahrenheit, or 98.6 Fahrenheit, you can calculate that. You know, convert. But we're not going to do any of that dipsy conversion from Fahrenheit to Celsius and Kelvin and stuff. You know, that's for like junior school, junior high. You know, that's for middle school. You know, we're more mature than that. All right, next question. Advantage to the Kelvin scale. Read this one carefully. Make a vote. Read carefully and think. And actually make a note of this question and the answer in your notes, because this is a teaching point that I want to review with you. The answer to this. Because this is like a strategy question for science strategies. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 70% of you got it correct. This is actually the best answer. Now, here's why that's important. And I've kind of alluded to it already. A temperature scale in which every temperature is positive, non-zero, is good because kinetic energies are always positive, and the average kinetic energy in a gas is proportional to the temperature in the Kelvin scale. Now, if you had to use Celsius, you'd have a much more complicated formula. You'd have to subtract 273 and all kinds. And Fahrenheit, even more complicated. You'd have to multiply by 5/9 or something. It'd be a mess. But for Kelvin, it's just, temperature equals a number times average kinetic energy. Kinetic energy average equals a different number times the temperature. And something similar is true for the pressure. And if you have a container, like you're filling up the tires at the gas station, so many PSI, that's definitely not metric, but that's what they have at the gas station, 32, 33 PSI. putting so much extra pressure in your tires, and that's a similar thing that tells you about the density and the momentum state on average of the air molecules inside the tires. Now, I want to talk about another thermal concept, and that is color and temperature. You could put something in the campfire. If you go on when I was a kid, we used to go on campouts for Boy Scouts, and then, my parents would ship me off to summer camp for the summer and get me out of town. And we go on these campouts, and when you're on a campout, you're always a pyro. You like throwing stuff in the fires, see if it burns and whatnot. And you could get, and if you find something metal, like we found this big piece of rebar out in the wilderness once. I don't know what it was doing out there. And we put it in the fire till it was red hot, and then we were burning our names and stuff. But you can get stuff red hot. And when it's red hot, it's hot. But there's stuff that's hotter than red hot. And then there's stuff that's cooler than red hot. Now here's a red supergiant. This is an actual picture of the surface of this star, Betelgeuse. It's the right shoulder of the Hunter Orion. Now Orion is visible. It's rising now in the east early in the morning. So I think. No, I take that back. It's rising in the east in the early evening now. So you should be able to see Betelgeuse later in the night. Orion. And Betelgeuse is the star that's the right shoulder, if you know Orion. It's a red supergiant star. It's super ginormulous, very big. But it's not that hot. It's cooler than the sun. The sun is actually hotter than red hot. The sun it's kind of a yellowish green color. If you look at the sun, from 17 light years away, it would look yellowish green. It wouldn't look red like this. It's a red supergiant. This is a little bit cooler. And you see those white spots in there? See this? See these white spots there? Those are actually sunspots on another star. They're cooler. They're white because those areas are brighter in infrared. Now, we can't see infrared, but we have infrared telescopes that can make this out. This is one of the few stars that's big enough and close enough that we can actually make out details. And it's not ultra high res, but we can make out some details, these two big sunspots on the surface. Most stars are so small, much smaller than this, and it's far enough away that we could just, we can see light, but we can't make out any of the surface features. We just see a pinpoint of light. And we can, analyze it and stuff. But this is, but that's actually, you know what that is? Those are convection cells. That's like, in the sun, the magnetic fields that form sunspots are all hooked up with convection, which is a thermal process. And the convection cells on the surface of the sun are, half the size of our planet. They're gigantic. And they're even bigger over here on Betelgeuse. It's phenomenal when they got this image a few years ago. Okay, here's cluster M13 through a good telescope. And on this display, you can see some blue. A lot of blue stars, they're even hotter than Betelgeuse. So blue hot. So there's hot, then there's red hot, then there's blue hot, and what's beyond that? Well, beyond blue and purple is ultraviolet, baby, and then X-rays. So if you see something that's bright in ultraviolet, it's not just hot, it's really hot. And that's what we see if we look at the SUN. Here's a picture of the SUN in ultraviolet. We see, so this is through a telescope that doesn't see any of the visible light. It's got a lens that only permits ultraviolet through. It's an ultraviolet detector. It doesn't pick up any of the yellows or reds or anything from the sun. You know, we got other telescopes that do that, but this one, ultraviolet, 17.1 nanometer wavelength. And this stuff, look at it. It's blue. Where you see it bright blue, that's the upper atmosphere of the sun at about 1,000,000 Kelvin. Really hot. But it's ultraviolet, so we can't really see it, so we give it a false color, blue. You know, we do other layers of the atmosphere of the sun. We color them green and kind of orangey. You know, you go to this website and you can see the SOHO spacecraft. This is from yesterday about lunchtime, about 24 hours ago. They took this. And they have pictures every day. You can go to the SOHO website, just type in SOHO and solar, and you'll find their SOHO website. You see daily pictures of the SUN. You'll see visible color, you know, kind of whitish. You'll see false color infrared, or false color ultraviolet, all kinds of colors. So this idea of colors, and guess who was trying to figure this out? Colors and temperature? Max Planck. This was his starting point, trying to figure this business out. Ultraviolet, certain temperature. Blue, certain temperature. Red, a little bit lower temperature. Infrared, even lower than that. And that's what he was working on. Now, let's get down to the nitty-gritty of heating and cooling. Now, we're going to go through a few concepts here and then dismiss. So let's get in some notes. Specific heat. This is the numerical measurement in the lab, you know, we measured in the lab, of how easy it is to heat up a substance, gram for gram. So for instance, and we anchor everything to the behavior of water. Just like the Celsius metric scale of temperature is anchored, you know, boiling point and freezing point of water. Now for specific heat, this actually defines a new heat unit, the calorie. The calorie is a metric heat unit. And calorie is the amount of energy it takes to raise 1 gram of liquid water by 1 Kelvin. All right, so now that could be a calorie from sunlight. And by the way, a calorie, this is a food calorie, you know, from eating French fries or whatever. That's 1,000 of these calories. These are called thermal calories. And a food calorie is 1,000 of these. Okay. Now, one of these thermal calories is 4.184 joules of energy. So that's the conversion. You know who figured that one out? James Prescott Joule. So it could be a calorie that you get from sunlight or any other, you know, like a flame or something. Any other heat transport method. So here's what you would write down. The specific heat of water, liquid water, is 1 calorie per gram per Kelvin. And the way that we would write that in an equation is this. C equals 1.00 calories per gram Kelvin. So every gram that you have, if you want to raise it by a Kelvin, it requires 1 calorie. And that's kind of the definition of calorie. Now, solid water is a little bit easier to heat up because the measured specific heat for solid water, ice, is 0.5 calories per gram Kelvin. So if you have a gram of ice and you want to raise it by 1 Kelvin, you know, from 265 to 266, you know, it's below the freezing point, 265 to 266, every calorie or every gram, it only takes a half a calorie. Right? So that's, and you could just have to measure it for every substance. And some are easy, you know, like ice, and certain things are tougher. But you can ask yourself, well, why is it different? Why is it easy to increase the kinetic energy of solid water, H2O ice, than liquid water? You know, liquid water has weak bonding. It forms droplets. It'll hold together. It'll cohere into a droplet, but it doesn't form the rigid crystalline structure that ice does. Right? And the difference is the average kinetic energy above 273 or below it. Above 273, liquid. Below 273, solid. And that means that the difference at 273 is whether your water has formed crystalline bonds, a rigid structure or not. Ice and liquid water at 273 Kelvin are perfectly happy together. They can't heat each other up or cool each other down. But something outside, if you turn on a flame or you shine the sun on it or something, then you can heat it up externally. But in itself, water at 273 cannot melt any more ice at 273. That's their boiling point. But what the ice has is crystalline bonds. Now, I have a phrase here, EPE, electrical potential energy. Those intermolecular bonds that form ice and differentiate ice from liquid, that is an enormous amount of electrical potential energy. Now, we haven't really studied the forces of electromagnetism yet, but we're going to. Now, before we dismiss, I'll just just let you know that other substances you're going to look up in a table. So here's a table. Now, I'm going to give you some homework tonight. We'll dismiss now. I'll give you a little tiny homework involving this table or something like it. All right? So you are dismissed. I'll see you on Thursday, and we'll continue this discussion.